and listeners. You are once again welcome to another episode of our weekly online chemistry class. We are still on season 7, and as discussed in the previous episode where we talked about atomic radius, I defined the term for you, gave you the 3 types of atomic radius that we have, and also explained how this periodic property varies both across the period and down the group of the periodic table. And I also told you point blank that the atomic volume cannot be used to measure the size of an atom. I gave you the reasons for that. In today's episode, we are going to discuss ionic radius, the last periodic property of elements. Ionic radius, by definition, can be defined as half of the internuclear distance between 2 ions of the same atom, in an ionic molecule or ionic solid. Take for instance, if you have sodium fluoride, if you write the structure of this as a demonstration, assuming this is a sodium ion which loses electron to a fluorine or fluorine atom to form a fluoride ion, and this is another sodium ion where we have another fluoride ion. So assuming this is the nucleus, if you want to measure the ionic radius of sodium, for instance, so that means you have to look for ionic salt of sodium, like sodium fluoride. If this is the nucleus of this ion of sodium, and this is the nucleus of this ion of sodium, if you measure the distance between the 2 nuclei and take the average of that value, you are going to have the radius of the ion. The same thing applicable to fluorine or fluoride ion. The ionic radius of fluorine is half of the internuclear distance between 2 fluoride ions in an ionic molecule. And it's similar to atomic radius. Ionic radius also increases down the group and decreases across the period. I want you to look at the general terms here. Where you have in period 2, lithium, beryllium, boron, carbon, for instance. A lithium atom has 2 shells, 1 electron in the thermal shell with 3 protons in the nucleus. A beryllium atom also has 2 shells, 4 protons in the nucleus, 2 electrons in the outermost shell. A boron atom also has 2 shells, 5 protons in the nucleus, 3 electrons in the outermost shell. A carbon atom also has 2, 4 electrons in the outermost shell and 6 protons in the nucleus, 2 electrons in the inner shell. If you look at a lithium atom, a lithium ion means lithium atom has lost its valence electron. And after losing the valence electron, the valence shell is completely lost. So this ion will have only 1 shell with 2 electrons, and the positively charged nucleus still remains 3, the nuclear charge. Beryllium ion means it has lost all the valence electrons, which are 2. So therefore, the nuclear charge is still 4, but also has 2 electrons in the outermost shell. For boron ion, we have B3+. 3 electrons in the outermost shell have been lost. So we still have 2 in the remaining shell and 5 nuclear charge. The same thing applicable to carbon for ions, where we have something of this nature, but 6 positively charged nucleus. So you can see that as you go across the period, the atomic size of the element, neutral atom, increases. But likewise, as you go across the period, there is increase in ionic radius. There is a decrease in ionic radius, since atomic radius also decreases across the period. Why? Because all the ions have the same shell and they have the same number of electrons. But however, they have different charges. So as you go across the period, more electron is being lost from left to right when you consider cations. But down the group, the reverse is the case. Ionic radius increases. Why? Because there is increase in the number of shells. If you look at group 1, where we have lithium, then we have sodium, then we have potassium. A sodium ion has only 1 shell. A lithium ion has 1 shell. A sodium ion has 2 shells. A potassium ion has 3 shells instead of 4 after losing its valence electron. So you can see that as you go down the group, there is increase in the size of atom, and therefore ionic radius of elements tend to increase. Meanwhile, there are some things that need to be taken note of. One, we observe that the ionic radius of cations are smaller than that of the neutral atom from which they have been obtained. Why? Because neutral atoms lose electrons to become cation. For lithium ion to be formed, the lithium atom has to lose its valence electron. So by losing the valence electron, a shell is completely taken off from the atom, and therefore the number of shells has reduced, so thereby reducing the size of the ion compared to the neutral atom. Another reason is that although electron has been lost, but the nuclear charge remains the same. We still have 3 positive charges in the nucleus. So that means the positively charged ion of that cation will feel more attractive force for the nuclear charge compared to the neutral atom, because the only electrons that are left on the ion will be more pulled to the nucleus as compared to the neutral atom. And that is why cations have a smaller sizes compared to the neutral atoms from which they have been obtained. Another question is that why are anions bigger in size than their neutral atom? For instance, we observe that an oxide ion has a larger size than neutral oxygen. A fluoride ion has a larger size than neutral fluorine. A carbide ion has a larger size than neutral carbon. Why? Because neutral atoms gain electrons before they are ionized to become negatively charged. So by gaining electrons, more electron is being added to the valence shell, and there is an electrostatic force of attraction between the electrons already present in the outermost shell of that atom and the added electrons. So that increase in electrostatic force of repulsion, not attraction, repulsion, tends to increase the size of the atom. Because the electrons that are present in the valence shell of the neutral atom, we have to create space for the incoming electrons to occupy the same shell. And as a result of that, although the nuclear charge remains the same, but adding electrons will increase the effective electrostatic force of attraction between the valence electrons and the nucleus of the atom. And that is why the anions usually have larger sizes compared to the neutral atom. Now, another thing is that we notice that ionic radius increases with decrease in atomic number and decreases with increase in atomic number. Meaning the higher the atomic number of isoelectronic ions, then the smaller the size. Take for instance, we observe that lithium ion has a bigger size than beryllium ion, which is bigger in size than boron ion, bigger in size than carbon ion. Do not forget that all these cations, they are isoelectronic in nature because they all have 2 electrons each and they have the same number of shells, although their sizes are not approximately the same despite having the same number of shells. Lithium has lost 1 electron to contain only 1 shell of 2 electrons. Beryllium has lost 2 electrons to have 1 shell of 2 electrons. Boron has lost 3 electrons to have 1 shell of 2 electrons. So the higher the number of electrons lost, so that means ionic radius is also a function of the charge and atomic radius. The higher the number of positive charges on the cation, the smaller the size. So here you can see atomic number 3, 4, 5, 6. As the atomic number increases, the size of the ion tends to decrease. So cations, their sizes is a function of atomic number as well as their charge. The same thing is applicable to anions, but in a reverse manner. Anions, the higher the charge in terms of negative charges, the smaller the size. The bigger the size. And that is also a function of the atomic number. If you look at period 2, where we have carbide ion, then we have nitride ion, then we have oxide ion, and we have fluoride ion. We discover that the size of this is bigger than this. This is also bigger than this. When this has atomic number 6, 7, 8, 9, they are also isoelectronic ions because they all have 10 electrons each. But you can observe that carbon has gained 4 electrons here to attain the octet electronic configuration of the nearest noble gas, which is argon. while nitrogen has gained 3 more electrons. So because more electron has been gained from carbon compared to nitrogen, you expect this to have a bigger size than nitride ion, despite having lower atomic number. Because the extra electron that is being gained by carbon make the electrostatic force of repulsion between the electrons already present in the outermost shell of the element and the electrons being added to be larger. So as a result of that, when you consider isoelectronic ions, you have to take care of their charges, whether they are positive charges they have positive charges or they have negative charges, which is a function of their atomic number. Another thing, I think I've said that we have what we call isoelectronic ions, and these are the examples that are given on the board. But generally, you can actually observe that all these properties are being strictly based on the main periodic elements. I mean the S and P block. We have tried as much as possible to isolate the D block and the F block elements. D block, for instance, we notice that all these periodic properties of D block elements are not generally as affected as the main as the S and P block elements. Why? Because the valence electrons in the of the main group element are found in different orbitals, which can either be S or P. And that differences in the orbitals where the valence electrons are found account for why their periodic properties tend to vary either from left to right or down the group. But for D block element, all of them, their valence electrons are found in the Ds of shell. So because of that, there is little or no difference in their periodic properties, starting from ionization potential, electron affinity, electronegativity, electropositivity, atomic radius, as well as ionic radius. So as a result of this, you are expected to be able to tell us the difference between ionic radius and atomic radius, and why are cations having smaller sizes as compared to the anions, as compared to their neutral atoms, and why are anions having larger sizes compared to their neutral atoms, then why are anions having larger sizes than cations of the elements in the same period in the periodic table. So these are the questions that needs to be answered by you as chemistry student. And I believe you have learned one or two things in today's episode. In our next episode, we are going to consider another thing entirely still under this season, and that might be the last episode of the season. Thanks for watching. Do not forget to subscribe to our YouTube channel and as well like and comment whenever you are watching our video. Thanks for watching, and see you again some other time.